I want to welcome you to advanced econometric analysis. You know, when people hear the word advanced econometric analysis, their mind is more about advanced. Okay. And even though it is advanced, it is also more of applied. And you will notice that quite a number of the things you did in advanced quantitative research, you will not do them. You will not do them here. Okay. You will understand the theories and the derivations and what goes into them. But more importantly, you will apply them and interpret them and publish a paper from this module. That's the whole idea. So by the time you finish the module, you already have a paper. And you can choose a paper on analysis. You can choose a paper you want to write related to your supply chain, blah, 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 blah. But at the same time, you're applying econometric methods to execute that research. And so you will notice that you're applying econometric research. It doesn't matter which industry of concern that you pick on. All right. So we've done all the housekeeping already, just some few things to be able to note. I know all of you, you know me already, so I'm not going to go through this. I wanted to participate during the synchronous live sections that I'll be doing. Read the core textbook. That is a book by Greene, Bill Greene. Okay, William Greene, Bill, his book is well known. But Trevor Cameron and Treveldi, they also have a microeconometrics book. I'll show you very soon. Read them and the suggested resources. Okay. Do a self-study. Do a self-study. Dig more into it. And the sort of questions and data and things I'll give you will force you to do a self-study. So do a self-study. Start your assignment work ASAP when I give it to you. Okay. You will have 3 of them for this, in addition to your project or publishable paper. There will be some continuous assignment, in between. All right. So these are some basic ground rules. Arrive on time. Arrive on time. Okay. Don't let me arrive before you arrive. It shows me that if you can master this module, you can master a lot of things. Okay. Use the laptops a lot. In fact, almost every day, try and come with your laptop, use a laptop a lot, and write notes, because you're going to use this note. You'll be surprised. You're going to be using these notes to teach undergraduates. You're going to use these notes to teach masters based on all that you gather from this. Okay. I have developed this, but I promise you, if you take this alone, it will become your baby, because this is an area where you can teach in economics. What we are doing, you can teach in economics department, you can teach in any business school, you can give it to those in humanities, psychology, political science. It cut across. They all use these models. They call them regression models, but this is in here, we call them econometrics. Okay, now these are the books. These are the top leading books in the world that you will ever in your life need when it comes to these topics. Now, who can tell, which of you can tell me what econometrics mean? What is econometrics? It comes from which 2 words? And what does it mean? Let's look at the etymology of the word econometrics.
Doc, I'll say in a layman's, from a layman's point, I will say the measurement of economics.
The measurement of economics. Yeah. Okay. What about you? What do you also think? What is the econometrics?
Prof, I will say it is the combination of economics and mathematics.
Good. The combination of
real life situation
and mathematics.
Yeah, thank you.
Who also has another idea about what you think is econometrics?
Oh,
Francis.
So, Doc, I would say is the use of statistical and mathematical models to estimate economic parameters and that can be applied to real life situations.
Good. So it's like each one of you is improving that of the other you know, on and on. Okay, so that's good. That is three things that come together to give birth to econometrics: mathematics, statistics, economics. That's it. Mathematics, statistics, and economics. The mathematics is a little bit, suppressed, a little bit suppressed. Okay, but Albert, I'm doing a recording already. Are you all right?
Oh, okay, so.
Yeah. So you have mathematics. I just want to be sure that it's going on. Mathematics, statistics, yeah, it's going on, and economics. Now, it doesn't mean that you must have knowledge of economics to be able to do this. I want to put that on cross. Okay, but if you did, it will help you. If you didn't, it will help you because you see that we are not going to apply it to economics. We are applying it to, like Francis said, we are applying it to real life data. It could be supply chain. It could be marketing. It could be engineering. It could be airline. It could be physics. But it could be quantum mechanics and several other things. It could be finance. So Brooks has actually written a book known as, Financial Econometrics. So you could apply it to everywhere. But the commonest book you use is the one by William Bill, Econometric Analysis. It's still the standard. It's still the top level books there. Introductory Econometrics is good for those who are beginners because it has a lot of, information. And then Applied Econometrics also gives a lot. Now, the book by Cameron is the blue one down here. Okay, it's a good one, but it's quite theoretical. Okay, so all of these, Harmless Econometrics is there, by Agresti. It's very, very good book. For panel data econometrics, you have a couple of books that I've also given here. But the main one is Econometric Analysis by Green. So these are the books that are, if you have them, you can teach. If you can understand this, you can teach any quantitative subject in the business school or in economics. Believe that, because these are the foundation. All right. So we're going to do some basic algebra. Do you guys remember when you were applying for your PhD, you were to calculate some basic algebra and some things? And I think even during your interviews, we did something like that. Okay. Yes, we are going to just warm up those basic algebra to help you to know that you need to have that foundational level of basic algebra so that you can teach and you can understand some of the things that you go through. So, if necessary, go back, take the book by Green, Appendix A, Section 8.1, all the way to 8.4 and 8.8.1. And you can understand the matrix notations that we use there. It will help you. It's a standard, it's basic to help you to know. And you are going to learn why we use matrices. Because matrices can compress so many things you would have written. For example, suppose you have a data set, and the data set is made up of the quantity demanded of a commodity, which is a function of price, a function of income, a function of complement price and substitute price, a function of population, a function of advert. All of these are multiple independent variables, and you can put them, and of course, they will have numbers for each one of them, numbers for each one of them, numbers for each one of them. These numbers could be coalesced into a variable called X, a complete matrix that contains the P, the Y, the O. So you can have this matrix, which is a series of rows, which is observations, and columns, which is the variables, all put into one. And that can now, we can always speak of the X, which contains each of these rows and columns. And it's easier to do that than to try and list all of them at a go. That is why matrices are very important, because they can help you combine, join, and disjoin things and be able to use them effectively when you want to deal with that. So that's why it's very nice to be able to know about matrices. So let's take a bit of a basic standard matrix that you know. Okay. But when you look at what I have here, is A matrix or is not a matrix? Today is a warm-up, so I'm not going to dread. I'm going to go slow and ask you basic things. Is A matrix or is not a matrix? Or what is A?
Dog, Anna here, dog.
Yes, Anna.
A is a vector.
A is a vector. Good. Is A also a matrix?
Yes.
Yes. To what extent?
It's also a matrix. It can be two rows, one column. Like I said, 2 by 1 matrix.
So it's a one-column matrix.
Yes.
And that is why it is what? A vector.
Yes.
Because a vector has two things. What are they?
Vector has
magnitude and direction.
It has a magnitude and direction. Okay. It has a magnitude and direction. So if you can take the two here, is it the X variable or the Y variable?
Is the X.
The X. So if you can move that on the X axis, you got a 2. And then you move the Y, which is the 1 step up. Okay. You can now create a hypotenuse. So you now have the magnitude, and then you now have a direction from the process. And that makes this. Iman, are you following so far? I'm drawing in the sky, but I hope you are following. How do you even create a pointer? Let me see. Oh, this one. I wanted the one that you can write. Where's the one you can write with? Anyway, let me use this. So if you have, I'm just going basic. So this is 2. Okay. And then you have this as 1. And so on the basis of that, we can say that from this section here to that is A. A is a vector. A is a vector. Now, it could be that this one is capital A, B, and then C. So the distance from A to C is small a, okay, which is generatable by the principle of Pythagoras theorem. You can get that small a as long as you know the distance from here to there and then from here to there. A is a vector that is also a matrix because it's a column vector. Now, so you've learned this and you did a bit of test on some of these things. If you look at A, if I can take a scalar by 3 and I multiply it by this A, you will now be able to generate this information of 6 and 3. Now, what do you think is the relationship between 6 and 3 and this 2 and 1? What do you think is the relationship there? What do you think is the relationship between that 6 and 3 and then that 2 and 1? What do they have in common? Francis?
So they have 3 in common.
They have what in common?
3.
Yes.
The
Yes.
number 3.
And we can say that they all have what? Apart from the number 3, they all have what? The same what?
Doc, can we say
They
they are both one column matrix?
They are all one column matrix. What else can we say?
the same direction.
The same magnitude and direction.
Yeah.
Yeah.
Yes.
They have the same magnitude and direction. So when two, vectors or two matrices have got the same magnitude and direction, we'll come and look at them. Because then there is something you can do between the two of them. If they have the same magnitude and direction, then you can do something very interesting with them. Okay. Now, what I just did is that I took a scalar and then I multiplied with this column matrix, and then I got this value. So it means that we can do vector multiplication. And there are 2 types of vector multiplication that we have. One is the inner dot, or the inner versus the outer product. Okay. What is the difference between the inner and then the outer product? Now, first of all, to be able to appreciate this, what is a scalar? I know it is somewhere in the slides that I will show you in the next couple of. What comes to your mind when you hear of a scalar? Albert, what did you say you did? You said you did mathematics, or you teach mathematics?
Yes, industrial mathematics.
So you're a champion in this, right? Ope? Or you put a bit of that, your industrial mathematics, on hold?
No.
Okay. So in mathematics and physics, what does the scalar mean? What idea does a scalar tell you?
Doc, I would say it's like a magnifier.
Mm-hmm.
Yeah, it's like a magnifier. That's
when you say, I can say that this is a magnifier, a 7-year-old child will not understand. You see, Emmanuel was, the moment he said that, his eye was looking up, then he started looking down.
So I would say it's a multiplier.
well, that's
Are you saying it or guessing it or what?
I think that's a better one.
Mathematician. Yes.
So it's I think I'll use the term multiplier because it makes it's only in magnitude, so you can compare it to like mass. It's you can talk about only the magnitude of it. There's no direction.
Why is very good. So it has a magnitude, it doesn't have a direction. Why?
Yes.
Why is that so? How is that different from a vector? Why? Take, for example, temperature. It has only a magnitude. It doesn't have a direction. Take, for example, speed. The speed. Speed has got a magnitude. It doesn't have a direction. Take, for example, mass or even energy. The same thing. So what is it that makes a scalar different from a vector? I'm only trying to break things down because today is our first lecture. Because in subsequent, you see me talking like that. Okay. Today is just for you to, familiarize. What is it?
No, I think a scalar can be. You can represent it on a number line. Put it up. You can visualize it by representing it on a number line.
Okay, good. So let's say that you have a vector, and then you have a scalar, and you multiply the scalar by the vector. What happens? Okay, so look at what you have here. which one is a scalar? Which one is a vector? Do you see my cursor moving?
Yes.
Okay.
Yes.
Which one is a scalar? 3A. Which one is a vector?
3 is a scalar.
And then
A is a
it's also
vector.
a scalar.
A is a vector.
Good. So now my question is that what does the scalar do to the vector? I mean, the only way you can answer this is just look at the end here.
Yeah, Doc, I would say it's magnifies or it's I don't know if that's correct. It's
I would say it magnifies. Okay.
yeah.
So what advantage do we get when you magnify? So take a speed. Okay? What is a speed doing to something that has a vector? What is temperature doing to something that has a vector? What is energy doing to something that has a vector? It stretches. That's what you are saying. It stretches, but it can also shrink.
Yes.
That's why I didn't want to only buy the magnifier. Because if it was 0.5, it will shrink. It will not magnify. What's the opposite of magnify? Shrink, right?
Shrink, yeah.
So what is the use of a scalar and that of a vector? A scalar actually increases or magnifies or shrinks that of a vector. And you will see that this is very useful, especially in engineering physics. Okay? When people are trying to, manufacture some things, especially things that are later compounded. Okay, so that was just a digression to let you know what a scalar means, that it is not the same as a vector because it doesn't have a direction, it only has a magnitude. So let's take an A and B, and both A and B are n by 1 vectors. And you now have A prime. What does A prime mean? We'll come back to it though. What does A prime mean? Now, these ones you should know. When it comes to the tougher ones, then you give it to Albert. What does A prime mean? There's a word.
Doc, the inverse of A.
You are almost there, but you are not there. Albert, the way you are smiling. Yes, Francis, what is A prime? You had that same thing in mind there.
Yes.
Yeah. Don't worry, if you have that same thing in mind, no problem. Albert, what is a prime?
I would say
you also had that in mind. What is the difference between the inverse of a matrix and the transpose of a matrix? Hey, is Godwell here? Papa Godwell.
Doc, I'm
Inverse
here.
and transpose.
Okay.
By the way, Godwell is not a mathematician, so I'm not going to. Inverse of a matrix and transpose of a matrix. What's the difference?
So the inverse is used to multiply the matrix to give an identity matrix, whereas the transpose takes the matrix from an n by m to an m by n.
I'm telling you, you have confused them.
Oh, I'm confused there.
I saw it in the faces of Nanajwa. Nanajwa, true or false? You help me here. True or false?
Doc, true.
Good. I'm a teacher. What is a simple difference between the transpose? We'll come to it though. But I just wanted to know that what you saw there was a transpose of a matrix. And not what, Albert?
not complement, but I was expecting to see the T on top. That's how I got a little confused.
So, Doc, that's what I also know, that normally it carries a superscript T.
Yes. So I was a little confused. I wanted to say complement, but I knew that it's not correct.
Because complement is in set
Yeah,
notation.
exactly. I was expecting to see the TCC on top of it, so that confused me a little.
So I can go and put the T there. I'll go and put the T there. But if you look at it, even though you don't probably, if you look at it, the example on the right will give you an idea, isn't it? That
Yes.
it wasn't column,
Yes.
isn't it, Francis?
Yes.
Yeah.
It was what? It wasn't a column, but it was a row.
A row, yeah.
And when you look at the B, it was rather in a what?
A
A
column.
column. And the B
It's
doesn't
true.
have the prime, what you might call capital T, which I agree. It's not all the time that it will be a capital T.
Oh, okay.
Yeah, Doc, you are right. It's clear in the equation.
Yeah.
Our attention was not there.
I know. Don't worry, we are here to learn. Okay.
Yeah.
Yes.
Now, that's why I said I want to go a bit slower so that you can appreciate these terms when you begin to see them. Now, if I take the transpose of A and I multiply it by B in this format here, I can now sum these together. Now, it is possible for me to sum them, but in the process of summing them, I will take each one element of the A transpose and multiply it by the element of the B and do the same thing. I can sum these things and I can eventually get B transpose A. It's the same thing. In short, A transpose B is B transpose A. It's a very beautiful, identity that you are seeing here. Okay. So let me just scroll up here. So if you have an I, which is a one, in this case, I prime or I transpose, which is a one row matrix. Not a one column matrix, a one row matrix. And if you have that one row matrix multiplying a column vector, a one column matrix, B. If you have that, you can still multiply that, but because the one is just one, which is a one element, and you sum that, you're going to get the same thing as the B, the vector B that you had. You will not get anything simply because it is one. This carries the idea of a dot or inner product matrix that we are discussing here. So that is the inner product matrix. The outer product matrix is this. You can see that the A rather comes first instead of the transpose of the A. And then the B prime is on the second element. So the first element, so we first said that A prime B is the same as B prime A. But the question is that the same as the opposite? So the inner product the first one we looked at, it will lead to a matrix that has reduced the dimensions, whereas the outer product will rather lead to one of the expanded dimensions that you have. So when you want a way to be able to memorize or remember it, you expand outward the inner product and then contract inward the outer product. Yes, it's very important to understand it because there are some levels of econometrics when you are doing, you have to appreciate the inner product and the outer product. Another concept of matrices you will have to learn is equality. Okay, equality. It's a very, very simple thing. For example, if a matrix A is equal to a matrix B, it is only equal to B if and only if the elements of A are the same as the elements of B. For every I here, which is a row by J column, for every row by J column. In other words, the element here will be equal to the element, sorry, the matrix here will be equal to the matrix there, provided the elements are the same. This is a clear equality. It doesn't matter whether there are many. So even if you have something like this, even if you have A, which is 2, 4, 3, 5. Okay, and normally we wouldn't say that A is equal to B, but simply because B is 2, 2, 3, 4, 5. So ideally, A is not equal to B, but because of the elements, you can say that we can say that A is an equality identity to B. Even though the letter A and the letter B are not the same, they are not A, simply because A elements and B elements are the same. A and B are the same. I think you get it. So have that rule in mind. Now we go to your transpose. You see, I'm again using the prime here. But I get you. When you get the note, you can change it to T so that you can remember it. Father Albert. You can
Matthias here.
So the transpose of a matrix is a very, very important thing because you use that a lot in regression analysis and in econometric analysis. So if you take the elements here, you have 1, 2, 3 in a row format. All you are doing is that you are turning the rows into columns. 1, 2, 3. And you are turning the columns into rows. 4, 5, 6. 4, 5, 6. But it's interesting to know that the transpose of A multiplied by its transpose is A. And again, it's very nice for you to take this example to be able to appreciate it. That the transpose of A. You have to take this one, multiply by that, and take this one, multiply by that, and then you will see that you get back the same A that you had. Then you can appreciate it. So when we say these identity, when we give you these formulae, don't just take them, take the element and work it out with your hand. Guys, what I mean is that work it. I don't want to do it because these are babish. Sit down and work it out with your hand. Okay, these are the elements of A. Okay, this is a transpose of A. Okay, I'm going to multiply it. Then you break it down. 1 times 1 plus this. Okay, 1 times 2 plus this. Then you multiply. Then you can now come back to get the A. You can now appreciate that A transpose multiplied by its transpose is A. The other thing is the additive property of that same thing in an expansive and simplification form. If you take the matrix of A and add it to B, okay, and you take the transpose of that, it is like just spreading the transposes, of A and B and then adding them as well. So understand the rules of transpose of a matrix. Next, let me just do something. All right, so let's look at a symmetric matrix. A symmetric matrix. What does the word symmetry come to your mind? It creates what idea? Symmetry.
So it means same or similar.
Okay, give me something that brings about the idea of symmetry. Anything.
Say information.
Information. Okay, under what circumstance? Yes. I know you are talking about.
Okay. Where we have to share information.
Yeah, under what circumstance can we talk about information asymmetry?
Where companies management have more information than the shareholders or other stakeholders.
Sorry, that is information asymmetry. I'm talking about information asymmetry.
Symmetry. Okay.
So, Doc, I think to add to what he's saying, that's when both parties have equal access to the same information, or the
That's it.
same information is shared
Yes.
equally between the two parties.
Good. So there's no
So what
hidden
A has
information.
is not different from what B has.
Good. So right now, between you and I, as far as advanced econometrics is concerned, is there information asymmetry or there's information symmetry? Nana,
There's asymmetry. There's
Asymmetry,
asymmetry.
Doc.
So
asymmetry. There's
even
asymmetry.
when we finish, we'll still have asymmetry because we have
We will still have a
different
big gap
information.
to cover.
Yes, yes. We still have some
But
gaps to
then,
cover.
but then, right now, between you and I, transpose of a matrix, is there information symmetry or there's information asymmetry? Be careful. Transpose of a matrix, which is right in front of you.
Mm.
Hmm?
There's information symmetry, Doc.
There's information symmetry. I know
Yes.
you're speaking for yourself. Okay. As to whether Nana will agree with you is a whole new thing. Can give you a question about it, then maybe you ask yourself, this one, I didn't think about it this way. Okay. So the best way you can explain symmetry is when you are standing in front of a mirror. Okay. And the distance between you and the mirror is the same distance between the mirror and the image. That is symmetry. And you outside of the mirror is the same you inside of the mirror. That again is symmetry. Keep that in mind. So what is a symmetric matrix? A symmetric matrix is that kind of a matrix which is a square matrix that is equal to its transpose. That is a symmetric matrix. It's a square matrix. A square matrix means that the elements within it are the same row by columns. It's a square matrix. And in such a case, then that kind of a matrix equals to its transpose. So if you have a matrix like A transpose is equal to A. Okay, because, and watch it, because the element of A being ij is the same as the element of AJI, even though I is not the same as J. In other words, even though the elements within are not the same, but in the positioning, the content are the same. And that is why I said that it requires that the matrix is a square matrix in that regard. When do we need that? We use that a lot because it helps in other engineering activities. Let's look at multiplication of a matrix. You now understand today what a scalar is. You now understand what a matrix is. You also understand what a vector is. Now, if you have an m by n matrix, and then you have a C, if A is an m by n matrix, and then you have a C, which is a scalar, and that is a 1 by 1 scalar, then when you multiply the scalar C by the matrix A, you will have CA. And that CA will be the same as AC. And that AC will take the properties of that of the matrix. And the C, which is a scalar, will be multiplying the element of the matrix, which is A in that set. So if you have a matrix multiplying another matrix, okay, when you have a matrix multiplying another matrix, that is a different thing. So let me ask you, what is a scalar matrix? Based on this, what is a scalar matrix? You can tell me. When you look at a scalar matrix, it is a special kind of what kind of matrix?
I'll say it's a special kind of identity matrix.
It's a special kind of an identity matrix. But before even it became an identity matrix, before then, do you guys remember what we said about a square matrix? What is a square matrix?
A matrix which has the same elements.
Good. Now, therefore, if you look at the definition I'm giving here by the scalar, okay, the scalar matrix would therefore be a specific type of the square matrix.
Yes.
Why? Why? Because when we look at all the elements, okay, on the main diagonal of that particular matrix will be equal. And when we say, I mean, going back to you, Emmanuel, when we say diagonal, I'm sure you know diagonal. And I'm sure you know what we mean by the diagonal of a matrix. We'll come to diagonal, but I know you understand what we mean by a diagonal, right?
Yes, Prof.
So when the diagonals are the same, and all other elements of the matrix are not the same, they are zero, basically. That is a scalar matrix. So if you have B here, if you have B, okay, and B is, having the elements of P rows and then Q columns, and then you have C, which is AB. Remember, we've already defined A as an M by N matrix. And now you have B being defined as a P by Q matrix. And C is a multiplication of the two. Okay? Then we can say that C is defined by an N equal to P matrix. Remember, we've taken the column here of the A matrix, and then we've taken the row here of the column matrix of the B matrix, okay? And we've indicated that the two are the same. And therefore, C, we can say that this C will become N by Q matrix. That is these right diagonals, okay, the N here and the Q, because we are multiplying them, okay? It becomes that M by Q matrix. That little C, the element of the C, will be as a result of the sum of the product of A and B. And this is a very interesting, analysis, because typically AB will never be equal to BA in this context. It won't naturally be equal. And therefore, we can say that if you have the transpose of C, it will be equal to AB transpose. Okay. And why is that so? Because we've already defined that here. However, that will also be the same as the B transpose and the A transpose. We already knew this from the previous slide that we indicated. So we can now also say that ABC transpose will be the same as the simplification of these individual matrices. Okay. And A plus B bracketed plus C is the same as A plus B plus C bracket. Okay. And then, of course, you can go through all of these other means to define it. What's the essence of all this? The idea is for you to understand that you can obtain a square matrix, okay, which we already have here. We can obtain that square matrix by multiplying an identity matrix by a scalar constant, which we have shown here, which in this case will be the A and B. You can obtain that identity matrix by a scalar constant. It's not like a vector, if you check it carefully. Okay? Unlike vectors, vectors will have both the magnitude and the direction. The scalar is only having a magnitude, okay? And so because it's only having a magnitude, it's possible for it to be able to use that to create that square matrix that we are talking about. All right, let's go to the last one, hopefully, a diagonal matrix. A diagonal matrix. Now remember, I'm going to ask you the difference between a diagonal matrix and a square matrix. So keep that in mind. I've already explained what a square matrix is. A diagonal matrix is a square matrix where all the elements of the main diagonal are 0. So now, what is the difference between a square matrix and a diagonal matrix? You can tell me. Guys, a diagonal matrix is a square matrix where all the elements outside the right diagonals, outside the diagonals, okay, or all the elements, not the diagonals, diagonal element, but then the off-diagonal elements are 0. How is that different from a square matrix? Yes, Aman.
So with a square matrix, it doesn't necessarily have to the elements outside the diagonal do not necessarily have to be 0.
Mm-hmm. What about the elements of the diagonal?
For the square matrix?
Yes.
The elements of the diagonal can be 0 or they can be any other number.
But then outside?
And outside too, for the square matrix, the outside can have any number.
Okay.
But with a diagonal, it's required that outside the diagonal, all the elements should be 0. But the square necessarily doesn't have to be 0.
Okay. So now let me ask you. A diagonal matrix is a symmetric matrix, true or false? In case you've forgotten what a symmetric matrix is, I can go back.
True. It's true.
It is true.
We can look at a diagonal as the mirror.
Yeah.
Sorry, I didn't hear. You say you can look at
a diagonal as a mirror.
Good. Yeah, it is true. So a diagonal matrix is a square matrix. Now, watch this. A square matrix is part of, a diagonal matrix is a symmetric matrix. A square matrix is part of a diagonal matrix, true or false?
No, please, can you say it again?
A square matrix is part of a diagonal matrix, true or false?
True.
I know what Nanaja is saying in her head. Maybe I'm family home to us. You got to have knowledge of these things, okay? You got to really have the knowledge of these things before you proceed. A diagonal matrix is rather a square matrix. It's rather part of a square matrix. A square matrix is not part of a diagonal matrix. A square matrix, okay, there can be other matrices that are square matrices but are not diagonal matrices. But as long as you're a diagonal matrix, you are automatically a square matrix. Okay, because a diagonal matrix is that of the square matrix where all the elements of the diagonals are 0. But you can have a situation where the elements that are off, Francis, you said it, the elements that are on the off diagonal are non-zero. In that case, they will not be diagonal matrices. They will still be a square matrix, but they will not be diagonal matrices. Albert, do you get it?
Yes, yes.
Good. Sometimes we write the diagonal matrix like this. No. Because the thing is that the other elements are off, the off diagonal elements are 0 anyway, so we just write it. Okay, let's go to identity matrix. What is that? An identity matrix is a special case of diagonal matrix. Now, isn't it funny? Because I already told you that a diagonal matrix is a type of, it's a square matrix. And now an identity matrix is a special diagonal matrix, which is a square matrix. Keep that in mind. What is a special, what is an identity matrix? An identity matrix is a special diagonal matrix where all the elements on the main diagonals are 1. Now, Francis, you can understand why it is a special kind of diagonal matrix, because you said earlier that the elements on the diagonals are not necessarily one. They can be any other number, but then the off-diagonal elements are 0. That's what you said.
Yes.
But when they are strictly 1, then they become what?
Identity.
Identity matrix. It's not m by n. It is an n by n, no by no. It's not mango by nano. So keep that in mind. So we have a typical situation here where if A is an m by n matrix, then an identity matrix of A is an identity matrix of is A identity matrix, which is equal to A, because everything in the identity matrix is 1. Okay. So let me ending with a trace of a matrix. The trace of a matrix. You can understand why I didn't want to go into all the details of this. What is a trace of a matrix? Let's see. Oops. Okay. So what is a trace of a matrix? Now, before you can appreciate this trace of a matrix, you got to understand what trace is. We always talk about trace only for square matrices. Only for square matrices. Now, remember what a square matrix is. So the trace of a square matrix is the sum, as you can see in the mathematics there, okay, is the sum of the diagonal elements of the matrix. So if you take the diagonal of, and of course it has to be a square matrix. If you sum them, so suppose the diagonals, and please remember the diagonals here are not an identity matrix, which are 1, 1, 1, 1. Says here there can be 4, 2, 7, 8. And when you add the 4 to the 2 to the 7 to the 8, when you sum them together, that gives you what? The trace of a matrix. So for you, so let me ask you, can we find a trace of a diagonal matrix? Yeah. Can we find a trace of an identity matrix? Yeah. So the trace is a very powerful concept. Okay? We call it invariant quantity. It doesn't vary. Okay? It remains the same, even if you change the basis, of which the matrix is represented. And I put it here that in physics, the trace of a matrix can be used to compute the expected value of an observable. So it's very, very useful to be able to, because you want to have that summation there of that particular observation there. Guys, when it comes to principal component analysis and factor analysis and structural equations modeling, they use this trace of a matrix. So trace of a matrix is a very useful thing. Okay? It gives you a precise and a concise, invariant way to capture information, very important information about a particular matrix, the particular property of the matrix, the behavior of the matrix, you can get it. Especially because you've got the capacity to what? To add them together. And this is very useful when we come to, like I said, PCA and other materials. So that is the end of our warm-up today. I put it here, this is a warm-up, okay, of our, okay. I mean, you will not really be studying matrices, but you have to know. That's the whole point. You have to know. You have to at least know that you know these matrices, especially because when you see the book trying to use these matrices, you will not be so much confused with it. Next time, we are going to look at the matrix differentiation. We'll look at the idempotent of a matrix. We'll look at the rank of a matrix. You look at the determinant of a matrix, and then we'll bring it together in a simple linear regression model of y and x, where y is a dependent variable and x is an independent variable. And a simple data set That will help you to bring all of this together. So, ladies and gentlemen, that brings us to the end of the entire caboodle today. The last time I mentioned it, somebody completed that sentence